An image is made up of many tiny pixels. Each pixel represents one small part of the complete image. Here, we have an 8 by 8 pixel grid. It is 8 pixels wide and 8 pixels high. To find the total number of pixels, we multiply the width by the height. 8 times 8 equals 64. So this image contains 64 pixels in total. The highlighted square shows just one pixel, one tiny part of the entire image. So remember, each square represents one pixel, and an 8 by 8 grid contains 64 pixels. The simplest bitmap image uses only 2 colors. To represent 2 colors, we only need 1 bit for each pixel. Remember, 1 bit has 2 possible values, 0 or 1. We can calculate the number of possibilities as 2 to the power of 1 equals 2. For example, we can define 0 as white and 1 as black. This means each pixel needs only 1 bit to tell the computer which of the 2 colors to display. So remember the key idea. 1 bit per pixel can represent 2 different colors. Here, we are using 0 and 1 to represent 2 different pixel colors. First, we need an agreed color mapping. In this example, 0 represents white and 1 represents black. Now look at the binary sequence, 0, 1, 1, 0. We convert each binary digit into its corresponding color. The first 0 becomes white, the next 2 ones become black, and the final 0 becomes white. So the binary pattern 0, 1, 1, 0 represents white, black, black, white. This is how binary values can be mapped to pixel colors in a simple bitmap image. The meaning of 0 and 1 is not always fixed. It depends on the encoding convention being used. In convention A, 0 represents white and 1 represents black. So the binary sequence 0, 1, 1, 0 produces white, black, black, white. But in convention B, the meanings are reversed. 0 represents black and 1 represents white. Now, the exact same binary sequence produces black, white, white, black. So the binary data has not changed, but the resulting image has changed. This teaches us an important rule. The encoding convention must be known before we can correctly interpret the binary data. Now, let's see how a binary pixel grid can be converted back into an image. In this example, we use a simple color mapping. 0 represents a white pixel, and 1 represents a black pixel. The computer reads the binary values row by row. In the first row, we have 0, 1, 1, 0. So this becomes white, black, black, white. The same rule is applied to every other row in the grid. Each 0 becomes white, and each 1 becomes black. Once all the binary values have been converted into their pixel colors, the complete image begins to appear. So remember, binary values can be converted into an image by mapping each bit to its corresponding pixel color. Now let's perform the process in the opposite direction. This time, we start with an image and convert it into binary data. We use the agreed color convention. 0 represents white and 1 represents black. Now we convert the pixels one row at a time. The first row becomes 0, 1, 0. The second row becomes 1, 1, 1. And the third row becomes 1, 0, 1. Next, we combine these rows in order. This gives us the final binary sequence. 0, 1, 0, 1, 1, 1, 1, 0, 1. So, remember, each pixel is converted into a binary value according to the agreed color convention. The computer needs a consistent order for storing the bits of a bitmap image. In this example, we start at the top left pixel. First, we read each row from left to right. When we reach the end of a row, we move down to the next row. So the first row gives us 0, 1, 0. The second row gives us 1, 1, 1. And the third row gives us 1, 0, 1. Finally, we join all 3 rows together to create one continuous binary sequence. So, remember the reading order, left to right and top to bottom. This allows the 2-dimensional pixel grid to be represented as a 1-dimensional sequence of bits. When binary image data is stored as one long sequence, the computer needs to know where each row ends. This is why the image width is important. Here, the stored binary sequence is 0, 1, 0, 1, 1, 1, 1, 0, 1. We are told that the image is 3 pixels wide. So the computer splits the binary data into groups of 3. The first row is 0, 1, 0. The second row is 1, 1, 1. And the third row is 1, 0, 1. These rows can then be placed together to reconstruct the original 3 by 3 pixel grid. So remember, the image width tells the computer how many pixels belong in each row. This helps the software reconstruct the correct pixel grid. Now let's create a simple binary representation of the letter T. Here, we have a 5 by 5 pixel grid. That means the image contains 5 times 5 equals 25 pixels. We use black pixels to create the letter T and white pixels for the background. Now we convert the image into binary, one row at a time. The first row contains 5 black pixels, so it becomes 1, 1, 1, 1, 1. Each of the remaining rows becomes 0, 0, 1, 0, 0. Finally, we join all the rows together to create one continuous binary sequence. So remember, we read the pixels from left to right, starting at the top row, and continue row by row until the complete image has been converted into binary. Now let's reconstruct an image from a binary sequence. We are given the binary data, along with some important image information. The image is 4 pixels wide and 5 pixels high. We also know that 0 represents white and 1 represents black. Because the width is 4 pixels, we split the binary sequence into groups of 4 bits. This gives us 5 rows: 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, and 1, 0, 0, 1. Next, we convert each 0 into a white pixel and each 1 into a black pixel. When all the pixels are placed in their correct positions, the image is reconstructed, and the final pattern forms the letter A. So remember, the image dimensions tell us how to split the binary sequence and rebuild the correct pixel grid.
With 1 bit, we have 2 possible binary values, 0 and 1. We can calculate this as 2 to the power of 1 equals 2 possible patterns. These 2 patterns can represent 2 different colors. For example, 0 can represent white, and 1 can represent black. So, 1 bit per pixel is enough when an image uses only 2 colors. But what happens when we want to represent more colors, such as red, green, blue, and yellow? 2 binary patterns are no longer enough. We need more bits for each pixel to create more possible binary patterns. And this leads us to our next important concept: color depth. Now it's your turn to create your own bitmap image. Start with an 8 by 8 grid. That gives us 8 times 8 equals 64 pixels. First, draw a simple picture, such as a smiley face, heart, letter, or shape. Next, convert each pixel into a binary value. For example, 1 for a colored pixel and 0 for a white pixel. Then, read the pixels row by row, from left to right, and create one continuous binary sequence. Now, give only the binary sequence and the required image information to a friend. Your friend can use those values to reconstruct the original image. This activity demonstrates an important idea. A bitmap image can be converted into binary data, and that binary data can be used to rebuild the image. Binary data by itself may not be enough to reconstruct a bitmap image correctly. Imagine computer A wants to send this bitmap image to computer B. Along with the pixel data, it also needs to provide some important information. First, the dimensions of the image. In this example, the width is 8 pixels, and the height is 8 pixels. Next, the receiver needs to know the color convention. Here, 0 represents white, and 1 represents black. Finally, it needs the actual pixel data, stored as a binary sequence. Computer B can then use all of this information to reconstruct the correct image. So remember, we need the image dimensions, the color convention, and the pixel data. Binary data alone may not tell us everything we need to correctly reconstruct the image.